For decades, sports nutrition has operated on a strict dosage ceiling. The consensus states that skeletal muscle can only utilize 20 to 25 grams of protein per meal for muscle protein synthesis. The prevailing model relies on the oxidation sink hypothesis. It posits that because humans lack a dedicated storage depot for excess amino acids, any protein consumed beyond that 25-gram threshold is simply oxidized for energy and wasted. But the foundation of that ceiling rests on a methodological constraint. The tracer studies that establish this limit routinely confine their postprandial measurement windows to a strict 4 to 6 hours. This chart illustrates the prior assumption. By cutting off observation at 6 hours, the data created a hard asymptote. It failed entirely to capture the prolonged digestion kinetics of larger protein boluses. The 25-gram limit is an artifact of inadequate observation times. The scientific community stopped its measurements long before the body finished processing the meal. In 2023, Tromelin and colleagues published a study that directly tested the 25-gram threshold using a methodological framework designed to track protein synthesis over a much longer time frame. The trial utilized 36 subjects, subjected them to resistance exercise, and administered 3 different protein doses: 0 grams, the standard 25 grams, or a massive 100-gram bolus. The differentiator of this trial was the timeline. The researchers kept the subjects under continuous metabolic measurement for an unprecedented 12 hours. This graph maps the new understanding of protein intake. The results demonstrate that the anabolic response to protein ingestion has no apparent upper limit. It scales linearly in both magnitude and duration with the dose provided. If tissue anabolism increases in direct proportion to intake volume, the existing clinical guidelines enforcing strict, frequent meal distributions are based on a flawed premise. Measuring anabolism over a half-day presents a severe physiological challenge. Researchers have to differentiate between the amino acids already circulating in the subject's blood and those originating exclusively from the experimental meal. To solve this, the study employed a quadruple stable isotope tracer method, requiring the production of intrinsically labeled protein to maintain steady-state conditions in the subjects. The researchers began by infusing dairy cows with carbon-13 tracers. This forced the cow's biological machinery to naturally produce milk enriched with L113C phenylalanine and leucine. By making the food itself the tracking device, the team could administer massive, varying doses of protein without destabilizing the precursor pool measurements. This precise tracking allowed physiologists to confidently map the metabolic fate of the meal hour by hour over the full 12-hour window. This graph tracks plasma amino acid concentrations. The standard 25-gram dose peaks and returns to baseline by hour 6, leading researchers to mistakenly conclude the anabolic window closes here. However, the 100-gram bolus keeps plasma amino acids significantly elevated for the entire 12-hour observation period. This state is known as hyperaminoacidemia. The data shows that ingesting a larger bolus dictates a slower, prolonged absorption rate in the gut, rather than hitting a physiological saturation point. That sustained availability of amino acids circulating in the plasma is the primary biological driver determining the prolonged muscle protein synthetic response. The gut does not discard the excess. It acts as a prolonged reservoir, steadily releasing amino acids to peripheral tissues for over half a day. We still have to address the oxidation sink argument, the belief that any excess amino acids in the bloodstream will be burned for energy. This scatter plot maps whole-body amino acid oxidation against total protein intake. The nearly flat line demonstrates the reality. While oxidation rates increase slightly with the 100-gram dose, they account for less than 15% of the total ingested protein increment. Contrast that minimal oxidation rate with the massive dose-dependent increases recorded in whole-body protein synthesis. Oxidation is not a physiological sink. Human metabolism preferentially routes dietary protein toward whole-body protein synthesis, regardless of how large the meal is. Skeletal muscle builds for 12 hours. Even those cellular on switches don't stay active that long. The primary kinase cascade responsible for triggering muscle anabolism after feeding is the mTORC1 signaling pathway. When you eat protein, mTORC1 tells the muscle to start building. This conceptual framework models the signaling. Following protein ingestion, mTOR phosphorylation rapidly peaks and returns to baseline. By hour 4, the mTOR signal has flatlined, yet the curve for muscle protein synthesis maintains a continuous upward slope for the subsequent 8 hours. Sustained kinase phosphorylation is not required to maintain muscle protein synthesis. The initial spike is enough to start the process. Once the cellular machinery is switched on, the rate and duration of synthesis are driven entirely by prolonged amino acid substrate availability. If the gut keeps delivering raw materials, the muscle keeps building. Moving to absolute metabolic fate, we can track exactly where the raw materials from the 100-gram dose end up after 12 hours. This stacked bar chart maps the distribution. By hour 12, 53% of the amino acids from the 100-gram dose have been released into systemic circulation. Looking at tissue incorporation, 13 grams of that bolus has been physically built into the skeletal muscle itself. To put that in perspective, exogenous amino acids contribute to 27% of total muscle protein synthesis in the 100-gram group, compared to just 9% in the standard 25-gram group. Skeletal muscle possesses a capacity to incorporate exogenous amino acids that exceeds what has been documented in human models. Humans are physiologically equipped to absorb massive protein boluses and utilize them for tissue building across prolonged absorption windows. This data directly impacts popular eating models, particularly time-restricted feeding and intermittent fasting protocols. The duration of the postprandial fed state is not a fixed window. It scales proportionally with the size of the meal ingested. This clarifies why consuming infrequent, massive meals does not compromise muscle mass. The post-absorptive, fasted state simply begins hours later than researchers previously assumed. Human metabolism is adapted to handle massive, infrequent nutrient influxes. This reflects the bolus feeding patterns used by predators in nature to sustain muscle mass. The 25-gram limit is a relic of restricted measurement windows. Protein anabolism has no biological upper limit. It is bounded only by the total dietary dose provided.